So this is certainly one of those topics where you're only going to be happy with it and understand it if you've had a wee bit of practice at trying to do these questions. So on page 32, you've got 3 questions which kind of mirror the examples we looked at on the previous couple of pages. So what I suggest you do, pause the video or do these before you look at the video. Have a go at these questions first. If you get stuck, you get stuck, but probably try to have a go first because that's going to help you figure it out. Then come to this video and I'm going to work through each one in turn. So hopefully you've had a go at that. So that's our first question. This should be what we call a standard example, kind of bread and butter kind of question. So I've got a reversible reaction here. What I might do at the start is just work out what the Kc is going to look like, because that's going to inform my working out. So it's going to be COCl2 over CO times Cl2. No squares or powers because everything's 1 to 1 to 1. Does this have units? Yes, it does, because if I work out the units, it's molarity in the top divided by molarity squared, which is overall molarity to the minus 1. So it's going to be moles to minus 1 decimeters cubed. So I do need to work out an equilibrium concentration. I can't just use moles here. And that's backed up by the fact they've given me a volume in this question. So with that kind of preliminary working out done, let's have a go with it. So I'm going to struck my wee table here. It's going to be COCl2 and COCl2. Each of those gets their own column. I'm going to have initial moles, reacting moles, equilibrium moles, and equilibrium concentration. That's everything I need. So let's look at what they gave me at the start. So a mixture containing 2 moles of carbon monoxide, initial moles, 5 moles of chlorine, initial moles. Do I have any product at the start? Nope, so it's going to be no moles as product at the start. An intense decimeter cube vessel, I'll need that later. At equilibrium, 1 mole of carbon monoxide remained. That's a little bit different to the example we looked at, because the first example had it give you the product at the end. So this tells me that at equilibrium, I've only got 1 mole of carbon monoxide, but that is more than enough to go off to work out the rest of the table. So if I look at the column where I've got 2 values, I started with 2 moles of carbon monoxide, I've now got 1 mole of carbon monoxide. That means that 1 mole must have reacted, because I've taken 1 mole away. Now, this is where I use my ratio, so it's a 1 to 1 to 1 ratio. If I used up 1 mole of carbon monoxide, it reacts 1 to 1 with Cl2, so I must have also used up 1 mole of Cl2. That makes 1 mole of COCl2, because it's 1 to 1 ratio, so I'm going to increase that by 1. So if I follow that through, 5 moles of chlorine take away 1 gives me 4 moles of equilibrium, and COCl2, start with nothing, add a 1 to it, gives me 1. So remember, I can't in this case just go straight to Kc now, I have to convert it into concentrations, so use concentration as number of moles over volume. Luckily in this one it's not too tricky to do because I'm dividing by 10 decimeters cubed. So 1 divided by 10 is 0.1, 4 divided by 10 is 0.4, 1 divided by 10 is 0.1. And at this point I now have got everything I need to calculate Kc. So Kc equals COCl2, which is 0.1, divided by CO, 0.1, multiplied by Cl2, 0.4. Type that into my calculator, ends up being 2.5. Now, if I'm being really careful, I'm actually only given one significant figure for all these values, so I probably should give that just as 3, rounded up. Stick the units in, moles to minus 1 decimeters cubed. Okay, so second question here. So we've got an equilibrium, this actually an esterification reaction we'll look at later on in organic chemistry. So it gives me grams and grams of 2 reactants and grams of one of the products, or grams of one of the reactants at the end. There's no volume here, which means maybe there's no units of Kc, so if I just check that, so 14 the formulas are quite long in this one. So top line CH3COO C5H11 times by H2O concentration over CH3COOH multiplied by C5H11OH. So looking at that, if that's moles per decimeter cubed, so on, that's going to cancel down. So there's no units of Kc for this expression, therefore I don't need to calculate concentrations, just can use moles. But that's not the trick in this question. The trick in this question is that you've not been given mole values. So it's quite nice in all the other questions, you just stick in a straight line, stick in the first line, this moles. I'm going to have to make the moles for myself by doing moles equals mass divided by RFM from the formula. That's a bit annoying, but I have to do it. So for the moles of ethanoic acid at the start, so that's CH3COOH, The mass of it at the start is 1.2 grams. Doing the RFM of it, so that's 12 plus 3 plus 12 plus 16 plus 16 plus 1, which is 60. 1.2 divided by 60 is 0.02. That's at the start. I'm going to need this in moles as well. That's at the end of equilibrium. Just do it while I've got ethanoic acid. So at the end, what I've got is 0.6 grams divided by the RFM, which is still 60, which gives me 0.01 moles. For the pentamonol, which is C5H11OH, number of moles of it is 1.1 divided by the RFM, which is 5 12s plus 11 plus 16 plus 1, which is 88. 1.1 divided by 88 is 0.0125 moles. So after a wee bit of annoying working out, I've now got enough to work out my table. So I'm going to construct that as normal. So I've got a big long formula here, which is a bit annoying. Initial moles, reacting moles, equilibrium moles, and I don't need equilibrium concentration because, as we said, there's no Kc units to this expression. So, initial moles. So I had 1.2 grams ethanoic acid. I worked out that is the same as 0.02 moles of it. I have 1.1 grams in pentamonol. I've worked out that that's 0.0125. I didn't have any of the product or either product at the start because it didn't tell me I had any product at the start. And what I've learned is that at equilibrium, I now go down to 0.6 grams of ethanoic acid, which is 0.01 moles. So from that, I can work out if I start with 0.02 moles of ethanoic acid, end up with 0.01, I've used up 0.01 moles of it just by subtracting that away from the initial value. Using my ratio now, it's a simple one because it's a 1 to 1 to 1 to 1 ratio. So if I used up 0.01 moles of ethanoic acid, I also used up the same amount of the pentamonol. Therefore, I've made the same number of moles because 1 to 1 ratio of the product and also the water. So converting those now into equilibrium mole values, so subtracting 0.01 from 0.0125 gives me 0.0025. And then from nothing, it's just going to be the value I've added. And those are my equilibrium mole values for this reaction. Sticking it into Kc, I end up with 0.01 times 0.01, because that's the two product values, over 0.01 times by 0.0025. That should come out as 4 exactly. Again, no units because units have cancelled down in this expression. Then on to the last question, which is similar to the third variation we looked at, where you're given a percentage kind of dissociation here. So we've got O3, which is ozone, in equilibrium with O2, which is normal and diatomic oxygen. So 2O3 is going to 3O2. In this expression, so maybe let's do Kc first. So Kc is just going to be concentration of O2 cubed over the concentration of O3 squared. Units would be moles per decimeter cubed divided by moles per decimeter cubed squared, which is just moles per decimeter cubed. Okay, so that's all sort of set up and ready to go. And because I've got units, I'm going to need concentration values, and they have given me a volume here to calculate that. So I need initial moles, reacting moles, equilibrium moles, and then equilibrium concentration I need in this calculation. So let's look at the initial moles. 1 mole of ozone. And it tells me that it's 30% dissociated. So 30% of that initial 1 mole has broken up and turned into oxygen. So 30% of 1 mole is just 0.3. So in other words, 0.3 times 1 is 0.3. Sorry. Yes, that's correct. So I've used up 0.3. Therefore, at equilibrium, that's turned into 0.7 moles of ozone. Using my ratio system's a wee bit tricky to work out. It's a 2 to 3 ratio. If I reacted 0.3 moles of ozone, divide that by 2 times by 3, that would mean I make 0.45 moles of diatomic oxygen. So again, using my 2 to 3 ratio, I've used up 0.3 moles of the reactant, I've made 0.45 moles of the product. I started from nothing because all I had to start was 1 mole of ozone, therefore I've made and now have 0.45 moles of O2. Again, at this point, I need to convert it into a concentration. Luckily, it's a nice easy one, just divide by 10 because that's a volume. So remember, concentration is number of moles over volume. So 0.7 divided by 10 is 0.07. Same for this one, it's going to go to 0.045. To turn it into my Kc expression, I need O2 cubed, so 0.045 cubed, divided by O3 squared, which is 0.07 squared. Into my calculator it goes, and I end up with 0.019. Thinking about significant figures, yeah, probably because just give me one, that's just one figure at the start, it probably is just one significant figure, so that would be 0.02 moles per decimeter cubed, which is the answer.